Hello everyone, welcome to today's webinar on finding the right data streaming architecture for your data needs. My name is Nikhil Kokar and I'm a solutions architect with AWS. I've been here for 5+ years working with customers to set up resilient and scalable architectures. In today's session, we'll understand how a modern data streaming architecture looks like and then dive deep into its subsegments. While doing so, we will generate an understanding of how the streaming data is ingested, stored, processed, and sent to its intended destination on AWS. We'll then have an example use case with a recommended architecture using the insights we have generated. So, a modern data streaming architecture is essentially comprised of 5 logical layers, and each of such layers is composed of multiple purpose-built components. The very first layer defines the data sources of the streaming data. The second layer defines the way in which we are ingesting that streaming data into our pipeline. The third layer defines how we are persisting the streaming data, followed up by the definition of data processing and the place of the destination. This architecture allows data ingestion, processing, and analysis for a high volume, high velocity use case for a real and near real time basis. In the remainder of our connect, we will have a deep dive understanding of all the different layers available. But for a quick 10,000 level view, the stream sources can be of multifold. They can be IoT sensors, they can be social media feeds, they can be enterprise applications with mobile and desktop applications. They can be distributed applications generating large amount of logs, which needs to be shipped, processed, and then made sense into an insights towards the later half of our discussion. From the stream ingestion perspective, there are multiple AWS services that are involved that are purpose built for the type of sources involved. We'll cover them in great detail, but at a 10,000 level view, we'll have like AWS IoT services, data migration service, AWS SDKs, which is also a direct way of integrating the downstream services with the API calls available. We'll also have certain agents which are purpose built for tailing certain type of data. And then we'll have a distributed open source connect framework with the open available connectors for our scope of discussion. But then once we have specified the type of source and the ingestion type, the next question arises is how are we persisting that streaming data? Because typically streaming data is of at least a milli MB per second, if not GB per second of throughput. So in that case, primarily three different possibilities come up. The very first is Amazon Kinesis data streams. Second is Amazon Kinesis Data Firehose, and then there is Amazon Managed Streaming for Apache Kafka, or Amazon MSK for short. We'll have a comparison of all the three possibilities in upcoming slides. Once we have persisted the incoming streaming data, we need to define the processing logic which we have to apply on that streaming data as per our use case. And depending on the capabilities and ease of use and comfortable development cycles per your use case, the processing type can change. So it can either be Amazon Kinesis Data Analytics for Apache Flink. There can be a serverless way using AWS Lambda. There can be a self-hosted, self-managed Kinesis client library or a corresponding Kafka consumer. Or there can be big data workloads that are running Spark streaming on either Amazon EMR or AWS Stream. So it depends on the use case and the type of processing we are trying to do and how open we are towards the ecosystem that comes up with these choices. Once we have specified the processing logic, the type of service, and the pipeline, we just have to specify the destination where the processed data will finally go into. Now, there are two different ways of thinking about this. First would be, should I directly use the processing logic to dump to a destination, or shall I buffer the flow from processing to my destination as per the use case? So we'll cover that in detail as well, how that matters and what benefits it will provide us. Cool. So diving deep into the streaming ingestion, the very first and the second layer of our architecture, and talk about a case-by-case basis. Let's say we have an IoT sensor which is generating like humidity data after every 1 minute of time. So there will be like a JSON created, which will say the device ID, the humidity value, and the longitude, latitude where the sensor is placed. Because the data is emitted every minute, you can imagine in an hourly basis, a device can send many JSON records. And if this is a large use case and it deployed globally, such devices can be like millions in count. Hence, your ingestion data would be very small but very frequent. For such use cases where the packet size is small but it is very frequent, the ingestion logic should be using either an MQTT protocol or an MQTT over WSS protocol. For all such devices which are using these protocols for data publish or subscribe, AWS IoT Core is a purpose-built solution which provides a message broker to receive such high throughput data of IoT devices, and it's a very natural way of integrating with these low memory, low powered IoT devices. Once we have an AWS IoT Core deployment done, the IoT Core broker then interacts with something called as AWS IoT rules, which enables these IoT devices to interact with AWS service. What that essentially means is if there is a record that flows into a particular MQTT topic, you can actually define a logic which say a certain type of message or entire topic data has to be streamed back to a choice of AWS service. Because of our scope of having streaming data, we can then use IoT rules to plug Kinesis data streams, data firehose, or even Amazon MSK to have that interaction going. But if the source is IoT sensor, AWS IoT Core is the best and the most native way to receive the data from such devices. Coming to different type of source, if let's say we have enterprise applications which are either mobile or desktop, and these devices are deployed globally and are generating a large amount of data as a whole, there are three possibilities of sending the data to our stream storage. First is a direct implementation of the API. So we can use any available AWS SDK that is compatible with the client environment, which implements the put record or a put records API call for Kinesis data streams. And there will be a similar Kafka producer for the Amazon MSK backend. But then a better way and a more robust way to send data from these applications would be via Kinesis producer library, which implements batching, aggregation, and retries on top of these existing API calls. So you'll still be triggering a put records API call onto your Kinesis data stream, but Kinesis producer library does some batching and aggregation in advance to make the ingestion cost efficient for a high throughput ingestion pipeline. And this is because for a provision mode of Kinesis data streams, a put payload unit is calculated by 25 kilobytes. So if your ingested record is, let's say, 50 kilobytes, two payload units would be calculated and hence billed accordingly. But if your record size is in mere bytes, or if let's say it's 5 kilobytes, it will still be rounded up to 25 kilobytes and counted as 1 minute. Because of that, aggregating those records into a 25 kilobyte payload unit reduces the number of payload units and hence the cost involved to put data into a Kinesis data stream. Kinesis producer library is one such way of doing that, where your ingestion patterns have small but frequent records. And the KPL aggregation essentially happens using a C++ code, which is then interacting with a Java wrapper from your environment. So the 10,000 level, what happens is, for an example, let's say you have 11 records and each of them has a size of 5 kilobytes. The total ingested data is sizing at 55 kilobytes. But then the most optimized way would be to aggregate them into 25 kilobytes payload unit. So record 1 to record 5 becomes one record, 6 to 10 becomes another, and then the remaining records become the third, which are then sent using a put records API call. So from Kinesis streams perspective, you are essentially getting three aggregated records, which are then required to be deaggregated and then consumed by a consumer downstream. But because instead of sending 11 records, we have sent three aggregated into chunks of 25, the costing of provision mode is efficient in that sense. For a different use case, if the source of streaming ingestion is relational database, the best bet would be to read from a change data capture source. So you will have like bill logs and transaction logs enabled onto the source. So it's a MySQL database, will have bill logs. For Postgres, there will be vol logs and so on and so forth. So there are essential two possibilities here. First is AWS Data Migration Service, which reads these change data capture events from those transaction logs. And then you can define a destination compatible with the endpoint. So you can have a MySQL to Kinesis data stream, a Postgres to Kinesis data stream kind of flow running. If let's say your choice is more inclined towards an open source alternative, Debezium connectors are available as an open source alternative, which can be deployed on a Kafka Connect distributed cluster of choice. Amazon provides Amazon MSK Connect as a distributed connect cluster on which these Debezium connectors can be deployed to have a similar experience, which will have a source from a relational database, which can then further dump to a Kafka topic of choice. The Kafka topic can also be an EC2 hosted Kafka or Amazon managed streaming for Apache Kafka, which is the managed version of the same open source project. Another type of workload would be your distributed applications generating terabytes of logs, which are then needs to be tailed line by line into individual records or a group of records, and then streamed to a destination Kinesis data stream. How that helps is if you need to analyze the logs or you need to ingest that to, let's say, an open search service or to any other analysis service like Grafana or Prometheus. In that sense, you need to first buffer it out into a streaming service. To do that, we have something called as Kinesis Agent, which is a purpose-built solution for such use cases. This is an agent which you can deploy in both Linux and Windows. And it's a standalone application which monitors file patterns. So you can, in the configuration, you will essentially provide a path where your logs are generated, and it will continue to monitor that file pattern, tail those files, and then using the tailed response, create records for Kinesis data streams or firehose for that matter, and start sending data to the destination. It also comes up with built-in file rotation capabilities, checkpointing, and even retries. So for all use cases where you have files which are being generated in a particular directory, Kinesis agent is a more natural way of getting such data out. But once we have got the data out and we have figured out how to get the data out, the choice next would be to decide where do you want to store that streaming data. Because if I have an MB per second throughput large request coming in from an application, it would not make sense to persist that into something like a relational database or a file system like EFS or even S3, because the use cases for streaming data is somewhat different. You need to kind of have a windowed way of querying the data, and then we'll need to have multiple iterations of those queries. So three possibilities of storing such streaming data is either a Kinesis data stream, a firehose, or Amazon MSK. So considering the type of stream storage, we can then have a comparison here. So the columns in this table comprises of the different possibilities available with the data streams, firehose, and MSK. The rows signify the dimensions which we are comparing. So Kinesis data streams comes in two flavors. There is a provision mode and then there is an on-demand mode. With provision mode, you need to provision the number of shards in advance as per your ingestion and consumption patterns. A single shard essentially provides 1 MB per second or 1000 record per second of data ingestion, and 10 MB or 10,000 records per call for data consumption. There is also a 5 transaction per second request on the get records call that is used to retrieve data from a single shard. But depending on these values, you can then calculate the number of shards required and then provision your stream accordingly. So that being said, with Kinesis data streams on demand, there is a possibility of adding or removing shards automatically as per your ingestion traffic. So there would be a by default starting point for the entire stream, not for a particular shard. So you'll have a 4 MB per second and a 4000 record per second ingestion rate for the entire stream, and then you can have at least twice of that from the consumption point of view. That is the minimum basic starting point for the stream. And then the stream kind of accommodates your ingestion traffic and kind of scales up to 2 times of your previous write peak, and tries to observe the pattern for last 30 days and then tries to increase it to 2 times of the previous write peak till the upper limit of 200 MB per second or 200,000 records per second. So Kinesis data streams on demand is a natural way for use cases where your workload is unknown or variable. Whereas data streams provision is the legacy way of creating streams which already have a defined workload and hence a defined number of shards for the particular stream AR. Kinesis data Firos in comparison doesn't require any resource allocation at all. You just create a delivery stream, define the destination where your Firos needs to deliver, and then the service takes care of the internal sharding mechanisms and how the data is spread across internally. The service takes care of it. But then there is a default throughput that is dependent on a particular region in which the service is deployed. If you are using the direct put way to interact with Kinesis Firos, certain region will have certain values. So let's say, for example, US East 1 gives you 5,000 records per second, 2,000 records per second, and requests per second, and 5 MB of data per second as ingestion. This is a default value and can be raised further via a support case with AWS Stream support. But then essentially there is no shard provisioning that is required from Firos perspective. From the scalability perspective itself, the scalability is managed by the service, and if the default quota is required to be increased, the support communication can happen accordingly. So these are three possible ways of persisting data into Firos or data stream with a provision or on-demand way. But let's say if your use case is more towards an on-demand on an open source basis. Let's say you already have an application which was interacting with an Apache Kafka deployment, and you don't need an application rewrite. Or if you have already in-house capabilities with Kafka. In such cases, Amazon MSK is the scope of review, and we also have two possibilities here: provisioned and serverless. So with provision, the user essentially has to decide the broker instance class and the cluster size as per your ingestion and consumption pattern. We do have a best practices documentation which includes a spreadsheet that helps you estimate the rough number of brokers and instance class required per your ingestion and consumption patterns. But then essentially that is the provisioning that is required on a certain expectation of your ingestion and consumption. If those values change, so does the provisioning also needs to be changed. And hence the throughput depends on the choice of broker instances you have specified. Not only that, once you have specified your broker instances, the spread of your partitions for individual Kafka topics also decide your overall capability of your producer and consumer. So if you have an uneven spread of partitions, the performance might vary accordingly. In terms of scalability, the provision cluster scales in minutes. There are APIs that can increase both the compute and the storage, but then the increase happens one way. You cannot reduce the number of instances or the storage of the cluster as of date. With Amazon MSK serverless, there is no need to specify broker instance class or the size of the cluster. It's essentially managed by the service. So for all unknown or variable workloads, Amazon MSK serverless is the starting point to begin with, because the cluster by default provides an ingestion rate of 200 MB per second. From consumption, you get a 400 MB per second possibility, and then you will get an instant availability of 5 MB per second of write and 10 MB per second of read per partition, so that you can scale as per the requirements. But then there are other inherent differences which needs to be considered before choosing each of them. As evident, the Kinesis suite of services are not open sourced. The Amazon MSK ones are managed by AWS and uses Apache Kafka features in a vanilla way. There's a certain minor version which is available in the user guide, which talks about the Amazon specific bug fix onto the Kafka version. Apart from that particular minor version, every other version is vanilla as per the open source Apache Kafka project. The maximum data retention for these stream storages vary. So for provision and on-demand Kafka Kinesis data streams, you have 365 days of retention. With Firehose, the retention depends on the way we are perceived. So uh, Firehose is intended to deliver data to a certain destination, and if that destination is not available, or if for some reason that delivery is failed, your failed deliveries are retried and then eventually discarded. So your retention indirectly depends on your number of retries and beyond which you discard the message. And these values change as per the destination chosen. So let's say if you have Amazon S3 as destination, your maximum possible retention comes out to be 24 hours, till which it will keep retrying till the put S3 put is possible. So it's not a direct value which you can modify. It's the way in which your retries are configured and the way in which your S3 or any other destination is configured. From MSK point of view, the provision cluster does allow a parameter which you can configure on the server side to have a retention period. But then that parameter will come into effect only if your EBS volumes attached per broker allows that amount of storage. The maximum volume size per broker is 1.6 terabytes, and then you can add more brokers to your cluster to have an overall cluster size as per your use case. But then the partition uniformness has to be maintained as per the best practices to benefit from the overall size. With MSK serverless, the maximum data retention is 1 day. There is a soft upper limit on the number of partitions, which is 120, and then there is a storage limit of 250 GB per partition, which is as compared to the provision way is a bit less. But then there are specific use cases where you would start with serverless, and then when you have finalized your workloads that are working fine in terms of provision, then you can go back to the Amazon MSK provision with the cluster configured. That is one way customers also evolve their journey with. In terms of pure latency values, Kinesis data firehose works on buffering logic. So once the data is ingested into the data firehose, you define a buffering hint which will say either that size of data or the time of data, whichever comes first is the point beyond which you will attempt a destination delivery. So if it's an S3, you will attempt an S3 port. So the minimum values are 1 MB or 60 seconds. So if somebody has to calculate a latency in terms of how much I can get from Firehose, the minimum would be 60 seconds unless you have ingested more than 1 MB of data in that particular time frame. From Kinesis data streams provision and on-demand perspective, the minimum latency is somewhere around 70 milliseconds with the enhanced fan-out feature enabled. From MSK point of view, it depends on the cluster provisioning and how your partitions are spread across the infrastructure, so that your consumer can poll from them accordingly. It also depends on your consumer performance, because unless the previous poll has completed, the next poll cannot happen. So if your downstream application is reading from that consumer, the lag between the two polls, which is not dependent on Kafka, but then dependent on the downstream application, will also be part of it. So that's why it can be considered low, but then it depends on how the infrastructure is provisioned as per the use case. That being said, once we have persisted the streaming data into our choice of service in our use case, we need to define how we have to process that data, and that is where our true business logic will kind of be applicable. We have multiple options wherein you can use these services to process the data, and we'll cover them one by one. So let's start with the very native way of doing this. Kinesis client library is a project available on AWS samples data repository, which is a way to consume from Kinesis stream in a distributed manner. We also have something called as Kafka consumers, which use the consumer group ID. And we also have K-streams, which is an API built on top of consumer API to read from Kafka topics. These projects can be deployed into EC2 instances and then either deployed in an auto-scaling group or as an ECS service or an EKS pod for that matter. And the scaling happens as per the choice of orchestrator or the auto-scaling group definitions. But then these individual hosts will have certain properties which allow them to talk to each other. So if we talk about Kinesis client library version 1 or version 2, each daemon will be booted up with certain configuration parameters. One such parameter would be an application ID. Then application ID by default is used to create a DynamoDB table in the same account for metadata management. So that metadata management is what allows each and every EC2 instance to be aware about each other. So if let's say you have a stream of 4 shards and you have 2 EC2 instances in the auto-scaling group reading from those 4 shards, the shards are evenly spread between the two. So there is a load distribution that happens. 2 shards are mapped to one instance and 2 shards are mapped to the other instance. And this happens because there is a concept of lease stealing and lease taking, and all that metadata is maintained into a DynamoDB table, which is by default named with the same application ID. So each worker boots with the same application ID and gets aware about the DynamoDB table and starts scaling accordingly. Similar concepts are there with the Kafka consumers, wherein your consumer group ID defines how your consumers are reading. And from the Kafka broker side, such consumer IDs are maintained by group coordinator, and that is what defines who gets the lease for which partitions. The concepts remain the same. Uh, the the service tries to maintain a 1:1 mapping between a partition and the consumer group consumer inside the consumer group ID. But then the scaling of these applications will happen as per the deployment choices. If it's an auto scaling group, there has to be a CloudWatch metric on which your scaling logics will be built on. If there is an ECS or an EKS orchestrator, then the native ways of scaling would be applicable. Next possibility would be AWS Lambda, which is a serverless way of reading data from Kinesis or Kafka. Kafka can be Amazon MSK or self-managed EC2 hosted Kafka as well. Essentially, what happens is when you provision an AWS Lambda with a trigger from either Kinesis or from MSK, event source mapping is created internally by AWS, which is the starting point of your get records or a poll request onto your destination streams. But then these event source mappings constantly trigger a poll to the Kafka or a get records to the Kinesis data stream, generate some responses, and then send it to your Lambda code that you have generated as a list of records. So this is a serverless way of reading data from these streams without managing the hassle of the dependent underlying library. The event source mapping for data stream for Kinesis data stream is actually an implementation of Kinesis client library only. So it can be perceived as a KCL with some default parameters. Certain of them are exposed as arguments once you are creating your triggers, not all of them. So if you're looking for ways in which you need more flexibility in your configuration, let's say you need minimum time between lease stealing, you need minimum idle time between reads, those kind of parameters you need to modify, which are available as setter methods in KCL. Those won't be available for AWS Lambda because those would be set with a certain default value, and then the event source mapping is booted with the KCL application in a distributed manner. But then all the necessary parameters which define the throughput handling capabilities are exposed as an argument once you are creating that event source mapping. So you would be asked to define the batch in terms of how much batch you need from the event source mapping into your invocation. If let's say there is an error while processing those records, there are possibilities of record splitting. So that let's say if you have 10 records coming from Kinesis and 5 of them takes majority of time, can actually split the batch into 2 so that your average execution time of your Lambda is reduced, and in that case your execution capabilities are not hampered. You can also have failed event destinations, so that if let's say you constantly failing, You can send that to a dead letter queue and then process later as per your convenience. And then obviously there are retries built in for from the event source mapping itself to read from the data from either data streams or from NST. Another type of processing is Kinesis data analytics. From AWS, we have two different flavors of the Kinesis data analytics application. One is for SQL, the other is for Apache Flink. For SQL, it's a legacy application that is still available for users which are already using this application, which allowed streaming data to be queried via SQL queries. So you can create an application, you can provide a SQL query which says, get me all the records on this particular data stream in terms of last 5 minutes, and then do a min max aggregates on top of this. It's essentially an experience in terms of SQL queries, but then the SQL query is converted into a logic which essentially triggers a get records call into a stream, gets the batch, does the number munching, and then emits it out to your destination. With the latest iterations, we have something called as Amazon Kinesis Data Analytics for Apache Flink, which uses the Flink operators in a more robust way. And this is a recommended way of interacting with streams for processing for new use cases. It also comes with something called as Analytics Studio, which provides you a notebook experience of developing the application, because the Flink application expects a jar which you will create using the Flink APIs. The SDK is available. You have to create a POM file for your application. Inside that, you will have all the dependencies mentioned. Then you will import those dependencies and start creating a class. You'll essentially create a source. You'll create some key byte modifications on the streaming data, and then you will have a sync of your choice. All that custom application logic is to be compressed and created into a jar, which is then imported into the application, and the application then runs that jar into a distributed manner managed by AWS. But then the whole development cycle can also be simplified if you are using the Analytics Studio, which provides you a notebook experience. So that you can have individual Zeppelin notebooks with cells wherein you can run your SQL, Python, or Scala code to interact with the streaming data, get the results into a subset value, and once you are finalized, you can deploy that studio application into a Apache Flink Kinesis Data Analytics application, and that would be a standalone application to proceed with. Diving a little deeper into the possibilities, the Apache Flink project supports over 25 operators. And what that essentially means is, in this scenario, let's say you have a Kinesis data stream and a Kafka. And if your jar is configured in a way, your code is written in a way that you are creating sources for both of them, logically there would be a data stream object of a data stream class created, which can then be either keyed by windowed or filtered as per our use case. So you can define a window of tumbling or a sliding logic using this streaming data, and then dump to a sink of choice. So Kinesis Data Analytics is particularly helpful for scenarios wherein you know that your streaming data has certain attributes and you want to filter it out, you want to aggregate on a certain key and the minimum operational possibility. So in that scenarios, once you have filtered it out, you need to dump it out to another stream or another topic of Kafka. For those scenarios, this possibility is the best suited one. It's the easiest way to get this done. That being said, you can always have a KCL application or a Lambda version of KCL, which does the same thing, but then the development efforts of splitting a list of records into different parts and then ensuring that your out of memory or out of runtime issues don't hamper the flow, that development effort needs to be taken care of. But if we are using the Apache Flink project, in those scenarios, you are benefited with all these operators for the particular use cases that you are looking for. Another way of processing stream is via the Spark streaming project. So Apache Spark provides libraries for streaming data use cases, which can be part of your Amazon EMR or AWS Glue jobs. Essentially, Amazon EMR is a managed way of running big data workloads. in which you will provision a cluster. You will define the number of nodes for your master, core, and task nodes, and then you will essentially run a Spark application with Spark streaming binaries, which will be reading from a stream, and then each batch is kind of created into a data frame of choice, using which you can then further do some downstream aggregations and then dumping to a destination of choice. But then if you're looking for an experience which is similar to Apache Spark, but then the provisioning is a concern in terms of getting to the right number of core and task nodes, AWS Glue is a serverless way of executing the same Apache Spark workload. It also supports Python scripts that can be executed as a job. The AWS Glue streaming job is essentially an equivalent way of reading from Kinesis data streams and from the Apache Kafka topics. So this is a particular use case for application developers who are more comfortable with the Apache Spark ecosystem. So if we compare the possibilities in a single shot, the Kinesis client library and the Kafka consumer APIs, these needs to be deployed into an autoscaling group for a distributed consumption logic. It cannot be a single point of failure. So you need to either have it in an autoscaling group or as an ECS service or as a EKS service with multiple pods. With Lambda, because the service itself is serverless, the infrastructure provisioning complexity is fairly low. You just provide your computation logic on the inherent data, and it's good to go from that point onwards. From Flink, you need to specify certain parallelism and parallelism per KPU parameters once you are configuring the project. And then the auto scaling will trigger automatically. But then there is certain aspects that are needs to be taken care of from provisioning complexity point of view. From Amazon EMR point of view, you need to specify your master, core, and task nodes, and then there are certain Hadoop level parameters, certain Yarn level parameters that are needs to be considered here that will define your overall instance class and count. If the ingestion rate goes high, your hardware needs to be scaled accordingly. There are ways to scale an Amazon EMR cluster. There is an auto scaling logic that you can define on a custom metric, or you can use the EMR managed scaling algorithm that now monitors multiple matrices to scale. But then essentially, it is not the most native way possible to read from a streaming data source as compared to the other possibilities. Same is applicable for AWS Glue. It's serverless, so all the hassles of provisioning and choosing the right instance from the initial go is taken care of. But then the auto scaling from Glue streaming workers is possible, and then it chooses a particular metric to scale the workers accordingly. So considering all of that, for use cases wherein you need configuration flexibility of your consumption, and you are already well familiar with Kinesis client library, you need to know all the getter setter methods, and you need individual read gaps configured from your point of view of your consumption. KCL on ECS, EKS, or an auto scaling group is the choice to be. Same goes with the Kafka ecosystem. If you are well familiar with the APIs and you need those flexible configurations, in that scenario, you can still have that deployed onto an auto scaling group or as an ECS or an EKS service. For Lambda, you would essentially would be looking for the most hassle-free way of consuming from the stream topics or data streams with minimal configuration possible, because there is built-in error handling, there is a lot of features available without managing or configuring the knobs available. For Flink, we have a very specific use case wherein you need to do a join or a merge of records in a windowed basis, so that you can use the ready-made operators available from our use case perspective. You can also create user-defined functions which can interact with any API responsing way. It can be an AWS service, it can be your own HTTP endpoint. But then those possibilities are relevant once you are trying to do a windowed query, which is joining multiple stuff while the streaming data is flowing in. From EMR and Glue perspective, the use cases are when you are well familiar with the Spark ecosystem and development considerations require you to stick with that environment for Spark streaming. and you are okay with the provisioning aspects involved, then Amazon EMR is the most configuration flexible option. Else you can consider Glue streaming jobs as well. If you want that Spark environment, but then you don't want to provision those core and task nodes over time. Comparing the costs involved, the Kinesis client library will run on certain hosts. It will be an EC2 instance, so there will be a fixed hourly spend of those EC2 instances, irrespective of the data available in the stream. So let's say you have periods of time where there is no data in the stream. Your EC2 will still run, your KCL library, your Kafka APIs will still run. They will still do a get records call or a poll. They will not get a response back. But then the EC2 is still running, so you are still paying for the hourly cost. AWS Lambda is a pay-per-use on events basis pricing, so your Lambda invocation will happen if there is a record available. You will still see get record calls and data stream from the event source mapping, but then if there is no record available, the invocations won't happen. So it's an event basis way of reading from the data sources. From Flink point of view, you also have a fixed hourly spend on the nodes that you configure for Flink using the parallelism and parallelism per KPU. So there is no direct input that you provide in terms of the number of nodes, but the value of parallelism and parallelism per KPU defines the number of nodes for your cluster indirectly. And you will be kind of paying with the hourly spend accordingly. And same goes with EMR as well as Glue, because with Glue you will have DPU units that will be consumed on an hourly basis, irrespective of the data that is flowing into the stream or not. Now that we have covered the streams storage, now let's cover and the processing logic. Now let's cover the stream destination, which is the last part of our conversation. You can consider a scenario wherein you have a Kinesis data stream which can be read from all the 5 possibilities. You can read from analytics, a KCL application, a Lambda function, a EMR Spark streaming job, or a Glue streaming job. And then once you have to choose a destination of your choice, let's say you need to create a data lake of your streaming data, or if you want to create a data warehouse of your streaming data for a larger use case where you need to do aggregations on a larger scale of terabytes or petabytes, or if you need to do a search capability onto the streaming data, you would choose either S3, Amazon Redshift, or Amazon OpenSearch service as a destination. Now, one possibility is you can have the native way of putting data into these services baked into your logic. So with the Kinesis Data Analytics, you can have a sink, let's say, which is compatible to put data into S3. That is a possibility. In AWS Lambda, you can import Boto3 and then you can use that to perform an S3 put. You can also trigger a copy command from Lambda as well. But then there are certain issues with this approach, because if the destination services, which is Amazon S3, Redshift, or OpenSearch service are not available, let's say your OpenSearch service has it goes in yellow or a red state, the attempts to put data into the destination will fail. Now, as a developer of the logic, the onus comes on to you to design your retries and the bufferings involved as well. So let's say if your OpenSearch service is getting overwhelmed with the streaming data, Lambda does scale accordingly as per your concurrency values, but then there is no buffering. Whatever is coming in is being dumped into OpenSearch, and if OpenSearch is not doing well in terms of the provisioning, there might be issues. So those buffering logics have to be baked into the flow somehow, so that you decouple the two flows. And then obviously for something like Apache Flink, there would be certain setter methods available with the particular sync of your project, to which you would be bound to, which may or may not be overlapping with your requirement. So to avoid all of these and to have a decoupled way of putting data, Amazon Kinesis Data Firehose also comes into picture here. It already came as a stream storage option. It also helps in choosing a destination of our choice. And how that works is, you, as a design practice, you use these services to get data from your streaming source. You do the processing, and then you put the processed data back to another stream or another Kafka topic of your choice. And from that destination topic, you then have Kinesis Firehose as the consumer for that process data stream. And then the Firos then provides you all those buffering and automatic retries capabilities from the Kinesis data streams ingestion data. So if let's say your use case is to do some key by value window operations onto your data stream and then dump into another Kinesis stream, that Kinesis stream will be consumed by a Firos. The Firos then decides the buffering logic of 1 MB or 60 seconds. And in that case, you are sure that your Amazon S3 uh, slowdown errors would be reduced to a lot extent, because now you are buffering your request instead of directly dumping it down to your destination. So that way, Firos kind of helps there. Uh, Firos also comes with a transformation Lambda function. So if let's say you need to do certain minimal ETL onto the data before persisting onto a destination, you can use a transformation Lambda. You can bake in your own logic and use that to either enrich the record with more or less values, or drop the entire record from the dataset, or skip the delivery for that data set onto your destination. All three possibilities are there, along with the buffering and automatic retries. With that said, let's cover the example use case and then implement these best practices onto such use case. So we have a use case wherein there is an e-commerce organization which handles large volume of transactions from customers. So the customers come to their website, buy something, and then use their accounts, their payment modes to pay for the transactions they have done. Uh, there can also be fraudulent activities in such use cases, because there can be fake accounts created, or there can be payments made from a credit card which is not owned by the individual who is doing the transaction. So to avoid that and to identify such use cases, the e-commerce organization needs a way to get alerted on such transactions. There is a need of near real-time detection of such fraud activities. Essentially, there is a requirement of email notification to be sent whenever there is a fraud transaction that happens. Uh, and then they need a monthly search capability on a report which lists all such fraud transactions, so that they can figure out, okay, hey, ABC user from a particular location is frequently doing fraud transaction in last 1 month. To answer such queries, they need a searchable report of such use cases. And then they also need a log retention in a cost-effective manner for audits of last 5 years or 10 years for that matter. The way the system is designed is that the backend application which receives the transaction request from their website or their mobile application generates an event for every transaction that is generated into Amazon Event Bridge. So somehow we have to figure out that from such transactions that are flowing in a streaming form, which one is fraudulent, and then send an email notification in near real time, and then generate reports and have log retentions applicable. So to answer such real-time fraud prevention use cases, we have an event bridge, and then AWS Lambda is integrated here to kind of, whenever there is a new event, a Lambda is triggered on an event basis as well to follow up with the on-demand flow of the pipeline. So this part becomes your stream source and ingestion, and Lambda has the request-based pricing. So if there is no event, there is no invocation, there is no pricing. If there is one, it's on an event basis only. So Lambda becomes a producer for your stream source storage. And in this case, we have chosen Amazon MSK because the organization was well equipped with the Kafka APIs, and they were comfortable with the configuration parameters, and they already be running Kafka in their non-cloud setups before. This hence becomes our stream storage, from where you can put data and reread from the storage till the retention period has expired. So you can pick an offset here and then move back in time till the retention period allows you to, and have multiple reads onto the stream storage. Because our events are flowing for every type of transaction, and our use case would vary as per the geography in which the use case is running. So let's say we're only targeting the North American market, or if let's say today we are only targeting the Asian market, all those use cases require key by filtration or segregation of streaming data to trigger your logics here. So Kinesis data analytics for Apache Flink is the best suited option here, in which you can do a keyed segregation of transaction and then process it over a window of sliding on a tumbling logic to create a batch. Now, once we have that batch created, you can then ship it through a user-defined function and engage something like Amazon Fraud Detector to detect if the transaction in that batch is fraudulent or not. And the service then responds back to the Flink, and the Flink gets an enriched response for the particular batch, and then the batch is then for that window is sent to the sink of our choice. Because we are segregating the raw and the processed transactions here, the destination for our sink is another topic of the Amazon MSK cluster. So this becomes our process storage location and also a stream storage type. Once we have that, from there we need to address all the three use cases. So the first use case is fraud prevention. Because my process data is in this particular topic of MSK, AWS Lambda can read from this particular topic, and whenever data is available, it just gets an invocation for a fraudulent activity, which triggers an SMS notification to send an email. This pipeline becomes event driven. Also, because we need reporting and logging capabilities, and because this is a high throughput use case covering multiple geographies, auto scaling at the Kinesis Data Analytics will take care of the scaling here. MSK can be considered as serverless for the time being, or we can provision it for the peak using the spreadsheet we discussed earlier in the best practices documentation. But then whenever data comes in, we need to ensure that our destination services, OpenSearch or S3, are not overwhelmed with their default quotas. S3 has a significantly large size of default quotas, but then OpenSearch depends on what type of queries are running, search queries are running at the point of time, and how we have provisioned the shards and all. So for all such use cases, there can be a distributed Kafka Connect cluster which has connectors that read from a topic and send data to a Kinesis data firehose. And then the firehose buffering will again come into a picture and then dump that data into OpenSearch service. So if your Amazon MSK Connect is auto-scaled, your MSK is provisioned well for the peak, your analytics, data analytics application is scaling as per your requirements, Lambda is event driven, end to end your pipeline takes care of your streaming use case for the scale. And then because Kinesis data firehose has a request based pricing as well. So if you have a firehose created and it doesn't receive a single byte of data for the entire day, there will not hence be a GB multiplied unit rate value for the day, and hence there will be no charge. You'll only be paying for whatever comes in through the firehose and then whatever triggers your transformation Lambda logic accordingly. There will be no hourly rate involved. So this also is a request-based pricing as with the Lambda setup here. So with that said, this use case covers the entire portfolio requirement for the customer. And we can very well replace the Amazon MSK with Kinesis data streams here, which is all in AWS way of doing it. And in that case, we can also get away from the MSK Connect connectors deployment here, because Kinesis can be directly consumed by data firehose, and in this use case, this pipeline further simplifies a bit. So that's it from the coverage of the right data streaming architecture and what are the moving parts and how we have to isolate, what are the thinking points when you are deciding to choose a particular service A over B. Hope this was helpful. Thank you for your time. Have a great day ahead. Take care, guys. Bye-bye.